Hello, welcome back. So, previously we looked at the power rule of differentiation, which basically said that when you want to differentiate something like x to the n, its differential is n multiplied by x to the n minus 1, right? Dragging down the coefficient, dragging down the power to the coefficient and subtracting 1 from it. So what you should be able to do right now would be something like the differential of 4x cubed, which would be 12x squared, and something like the differential of say 3x squared, which would be 6x. Now once you know this, what comes up next is the different combinations of these. So what if I want the differential of something like 4x cubed plus a 3x squared? Or what if I want something like the differential of 4x cubed minus a 3x squared, right? And what if there's a multiply sign in between or a dividing sign? Right, so let us first look at the case of plus and minus, then we'll get to multiply and divide. So let's say there's some function which is equal to 4x cubed plus a 3x squared, and you want its differential. Right, so ignoring the differential part first, let's just look at what the function really says. So if I have my graph, and let's say this is, let's take this as 3x squared, and let me draw something like this. Let's say this is 4x cubed, right? So what this function is really doing is that at a certain point in x, it is taking the value of 4x cubed at that point, and it is also taking the value of 3x squared at that point, and it is adding them together. So for example, if I take, let's say, if I take x as 1, let's take it over somewhere over here, somewhere, let's take it here, and let's take 2 instead. So when my x is 2, the value of 3x squared would be 3 multiplied by 4, which is 12, right? And the value of 4x squared would be 4 multiplied by 8, which is 4 multiplied by 8 is 32, right? So y equals 4x cubed plus 3x squared would simply just add these two. So 32 plus 12 is 44. So when x is 2, your y of your this graph would also be 42, and so the graph would look something like this, keeping in mind that it's really just adding the y values of both these graphs. Right, so coming back to our original question, what is the differential of 4x cubed plus 3x squared? So what you can actually do is you can make these sort of separate. You can divide this into the differential of 4x cubed plus the differential of 3x squared, right? So the differential of 4x cubed plus 3x squared is the same as the differential of 4x cubed plus the differential of 3x squared. The differential of 4x cubed would be 12x squared, and that of 3x squared would be 6x, right? And when you look at the graph, this should sort of make sense. So for example, at some point when I take the dy dx of 3x squared, so for some change, some small change, there is some change in x, right? And similarly, for that some change, there is also some change in that of 4x cubed, right? So remembering that y equals 3x squared plus 4x cubed is really just adding both of them. So when you take some dx, the total change in y would be the change in 4x cubed plus the change in 3x squared, right? So this is why you can write them separately as such that it's the differential of 4x cubed plus the differential of 3x squared. right? And of course, if there was a minus sign over here, this would also be a minus sign, and so would be this, right? So whenever there's whenever you have even many terms, not just two, of course, for many terms, whenever you have plus or minus, you can just differentiate them separately, right? So let's come to the case of multiplication, where we can apply the product rule. Before that, I would need to tell you something about e. So e to the, let's say e to the 2x is some function, and it is such that its differential is 2 times e to the 2x, right? Generally, for any e to the ax, its differential would be a multiplied by e to the ax, right? So what if you have something where two things are being multiplied? So for example, what if there's 3x squared multiplied by e to the 2x? How do you differentiate this? Right. So let's take a rectangle, and if you're coming from the previous video, this would perhaps be somewhat similar to the power rule. So let's take a rectangle whose one side is 3x squared and the other side is e to the 2x, and the y value is the area enclosed by the rectangle. So 3x squared multiplied by e to the 2x. Just to give you an example, let's say when x is 2, this side would be 3 multiplied by 2 squared, and this side would be e to the 4. So your area would be 12 e to the 4. And of course, if you put 2 over here, this would also give you 12 times e to the 4. Right. So let me draw a bigger rectangle. Right. So let's say this is some 3x squared, this is some e to the 2x, and let's say I increase my x by some small dx amount. So now this is some 3x squared plus some dx, right? So till here, this is your own original 3x squared plus some change in 3x squared, which is bought by some change in x, right? And similarly for e to the x, when I change my x a bit, when I increase my x a bit, there's also some increase in e to the 2x, right? D just means small change, by the way. So this is e to the 2x. So when I complete my rectangle, what I could see is that the change in area, or in other words, the change in y, is this thing plus this thing and also plus this thing, right? So when I change my x a bit, this is the resulting change in the y value, right? So let's write these down. So the change in y, let's write with white, the change in y is 3x squared multiplied by the change in e to the 2x, right? Because this is its one length and this is the other length, plus the e to the 2x multiplied by the change in 3x squared, right? Because this is one side and then this would be the other side, plus oops plus the change in 3x squared multiplied by the change in e to the 2x, right? So now I have some equation for the change in y. I can divide it by the change in x to get the differential. So the change in y over change in x would be 3x squared plus the differential of e to the 2x plus e to the 2x plus e to the 2x multiplied by the differential of 3x squared plus the differential of 3x squared multiplied by the differential of e to the 2x. Now realize that this portion, which corresponds to this small area, is a very small change. It is a very small part of the whole change. And the fact of the matter is that we can actually ignore this change, because dy over dx is actually the value that you would approach as dx, as, let me zoom in, as as dx is approaching 0. So your dx, your change in x, is getting smaller and smaller, and hence this value would also get very very small, right? And for smaller and smaller changes in x, ignoring this value would have lesser and lesser importance, right? That is, if you ignore this and just take this, as your dx is getting smaller and smaller, this would be a better and better representation of the actual value. And it is also just to note that here it may look like I took some big change, but in principle dx is essentially a very small change, right? So we can ignore this simply because it would be a very small value, a very small change, and ignoring this would give us an approximation that gets better and better as dx approaches 0. Right, so it turns out that my dy over dx, where y was actually 3x squared multiplied by e to the 2x, is this thing. 3x squared multiplied by the differential of e to the 2x is 2 times e to the 2x, plus e to the 2x multiplied by the differential of 3x squared, which is 6x. Of course, I can expand it to 6x squared e to the 2x plus 6x e to the 2x. Now, the thing that is to notice is in the pattern over here. Right, so when you look at this pattern, you'll realize that it follows a pattern such that you take one of them multiplied by the differential of the other, plus you take the other multiplied by the differential of the previous one, right? So in general, for differential of any, say, uv would be u v prime plus v u prime, where v prime and u prime are just the corresponding differentials, right? And this is what we call the product rule. Whenever you have two things multiplying and you have to find the differential of it, this is how you could do it, right? And by means of this square, it should sort of make sense, right? And just to look at our last example of the quotient rule. Right. So the quotient rule deals with stuff when you have a division in between. So for example, if you want to find the derivative of any u over v, right, where u is the numerator and v is the denominator, right? So what if I want the differential of, say, 3x squared over e to the 2x, right? So the quotient rule says that for any u over v, its differential would be v u prime minus u v prime over v squared, right? So here my u would be 3x squared, my v would be e to the 2x, so my u prime would be 6x and v prime would be 2e to the 2x. So if I want to differentiate this, it would be v u prime, i.e. 6x multiplied by e to the 2x minus this to this, so 2e 2x 3x squared divided by v squared, so e 2x squared, right? And whatever this turns out to be, when you simplify and stuff, this is what the derivative of 3x squared over e to the 2x would be, right? So that's all for today, right? So see you in the next video. Bye bye.